Hello, welcome everyone to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Richard, and with the producer Hector Salas, we are going to be your guides during this virtual trip in the Silla Observatory. So, just a little bit about me. I am one of the tourist guides of Paraná Observatory, actually, for more than 10 years. I have several years of experience in astronomy outreach and education, and one of my personal hobbies is astrophotography. But as I told you before, I am not alone. I am with the producer Hector Salas, and he will help me with some questions we can receive during this streaming. How are you, Hector?
Hi Farid, I'm happy to be here once again. I'll introduce myself. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related to the circumgalactic medium. We can think of this as the environment that immediately surrounds galaxies. And I started as a tour guide in Paranal Observatory in 2019 while I was doing my master's in the University of Antofagasta. And as you said, today I'm going to be the producer and I will be checking out the comments. And so if you have any questions, any doubts, please send it. And we'll have a couple of instances during the tour to answer them.
Okay. Yes, thank you very much, Hector. So, yeah, please remember you can send your questions or comments during all this streaming, and later we will have some time to answer them. Okay. Okay, so we are going to start immediately with this virtual experience. And please don't forget to share this experience in case you like it. You can do it with share buttons on Facebook or YouTube. Okay, so we are going to start talking a little bit about the organization, about what is ESO. Well, ESO is an intergovernmental organization composed of 16 member states. So its headquarters are located in Germany. Also, Australia has joined ESO, but in this case as a strategic partner. Chile is the host state and is the home of all ESO observatories. Um, from the 60s, and with those objectives in mind, ESO did choose one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So around that time, Chile had started an exploration campaign of several sites to attract international observatories such as ESO to our country. So in this case, Chile offered its territory, and ESO did choose the areas that were more suitable for an observatory. So the mission of ESO is essentially to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. We are going to see a picture with the three observing sites of ESO in Chile. So first we have the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT. The VLT is right now the visible light, the most advanced visible light telescope on Earth. In the future, near Paranal, we will have the Extremely Large Telescope, or ELT, and this will be the largest visible light telescope on Earth. And near there, near Paranal as well, we will have the CTA, the Cherenkov Telescope Array, an array of telescopes, in this case, focused on capturing gamma rays. We also have Chajnantor, and this is the site of the ALMA radio telescope. So in this case, ESO is part of this radio astronomy observatory alongside other international partners. And last, we have the place of our visit, La Silla Observatory. This was the first observatory of ESO in Chile. This is located in the Coquimbo region, in the north of Chile, and around 2,400 meters above sea level. So we are going to visit this place during the next hour. Okay, so we are going to start this trip with a view of Europe. So with this view of our planet, And we are starting this journey in Europe because you need to remember that ESO is an European organization. And in this map outlined in white, we can see the different states, I mean the ESO member states. And Chile is participating as the host state and is the home of all ESO observatories. So to know more about them, we are going to travel to the Andes Mountains in Chile. So now we are moving around the Atlantic Ocean, and I can tell you a little bit more about the mission of ESO. So you need to remember and you need to understand that the work of ESO is about imagine what type of instruments we need to study the universe. And they need to design the pieces, to build the telescopes, and to operate those telescopes um, to, to take care of the observation request from astronomers from all the planet. And in this case, we can incentivize the promotion and cooperation in the astronomy field. Okay, we are almost there. We are going to visit a very amazing mountain, and you can see basically several several mountains with domes. Okay, you can see the shape of this mountain top. So this mountain top is very similar to a horse saddle. So that's why we have this name, la silla, because la silla in Spanish is chair. So in this case, we are talking about not a regular chair, but it's a horse saddle. Okay. Okay. So now we are looking at a drone view of La Silla. So we are traveling to the different telescopes there. And you need to remember in this case that La Silla was chosen by the astronomical community at the beginning of the 60s. La Silla has a great number of clear nights per year, a quiet atmosphere, a dry atmosphere, and dark skies, far away from artificial light sources, I mean light pollution. This observatory was inaugurated in 1969, and some of the telescopes that you can see here are not in operation anymore. Right now, we have 10 telescopes in operations, and two of them are operated directly by ESO. The other telescopes are belongs to other institutions, and ESO are providing support. So you can see in this case how we have been visiting the different telescopes. You was able to see the names of the telescopes, and the last one in front of you now is the biggest one, the ESO 3.6 meter telescope. Okay, so now we are going to explore a little bit more about them. And in this view right now, you can see this perspective, right, of um, of the telescope. Hector, do we have the chance to look at the full view or something?
Yeah, I'm not entirely sure why it's not in full view. I'm trying to
Okay, maybe I can
maybe it's an
enlarge a
issue
little
with
bit.
your window. Uh,
Yeah, maybe. Okay, okay. Let me do something here. Okay, maybe we can continue just right now. Okay, so in this view, you can see the biggest telescope in La Silla. I mean the 3.6 meter telescope. Okay, and next to it, we have another important telescope right here. We have the New Technology Telescope, the NTT. Okay, so the NTT um, is the new technology is a very important telescope because the acronym New Technology Telescope means that in this telescope we were using a new kinds of technologies and developments, and some of those developments were later applied to, for example, Paraná. Okay, so this is why uh, this telescope is very important here. Now, from this view in 360 degrees, we can see the other telescopes in the distance. Okay, So you can see that in this observatory we have several domes, okay, and this is a panorama of the Atacama Desert. We can see that this is a sunset here. We can see the sunset there, and I know that you have let's say some clouds there. But as I told you before, we have a very good average of clear nights per year, around 280, something like that. And later in this virtual tour, I will show you a night view from La Silla, and you will see how how it looks a dark night in the Atacama Desert. This one is a former radio telescope. It's not in operations anymore, and here you can see the east, and you can see the Andes Mountains. Okay, so we have a full view of this beautiful place. So now we are going to explore first the 3.6-meter telescope. Okay, so let's take a look, and here we are. So in this case, you can observe the interior of the 3.6-meter telescope. Okay, so this one is very high. Sorry, it's a very big telescope, and you can notice here. I will try to show you the dome. See, and you can see that this is the dome. It's very impressive, and just to give you an estimation, well, from the first floor to the dome, we have 25 meters, okay? And all the structure of this telescope equals to a 7-story building, okay? So it's very, very big. The name of this telescope, the 3.6 or the 360, is a reference to the diameter of the main mirror, the primary mirror, okay? So the main diameter is 3.6 meters or 360 centimeters. This telescope, around the 70s, the mid 70s, was one of the largest telescopes on Earth. Right now, we have a very important instrument with this telescope. We have the HARPS instrument. HARPS is basically an exoplanet hunter. Okay, so we are trying to look for new planets orbiting other stars, and we are trying to do this. With the instrument we have here in the 3.6-meter telescope. Okay, now in order to take a look at how big is this telescope, I can show you that there is a person there. Do you see? So we have an idea now of how big is this instrument, okay, and this telescope. So in order to understand more about the telescope, I will display a picture, and you can take a look here, because we have some important components of this telescope. So for example, in dark blue, you can see the main structure holding the telescope. This structure is called the mounting. Okay, the mounting is working as a big arm to support the telescope and to provide, well, for example, the energy. So we are trying to provide everything from the mounting. Okay, now over this arm, and parallel to the Earth rotation axis, the telescope is moving to follow the objects in the sky during the observation. Now, if you look here in light blue, we have the telescope's body. So essentially here you have the main mirror, okay? The main mirror is here, the 3.6-meter mirror. And the secondary mirror is here in this tubular structure here. Okay. Now, where is the primary mirror? Well, the primary mirror is not visible actually because it's covered right now by its protection system, this thing. Okay. This black structure is a system of tabs that can be opened or closed to protect the mirror from dust or moisture when the telescope is in parking position. I mean, when it's not working. Now, in the tubular structure, in the black tubular structure here, we have the secondary mirror. The secondary mirror will concentrate the light collected by the primary mirror, and the light will be reflected to be received by the instrument. So essentially, when you have the light coming from a star, the light is going to the primary mirror first, and this mirror is concave. Okay, so it's like a spoon. That means that when you have the light here, the light is concentrated and is reflected to the secondary mirror and is reflected again. And this light is going to pass through this hole in the center. Okay, so essentially the physical light will be received by the instrument. And this is the instrument I was talking about before, is the HARPS instrument. Okay, so this is essentially what happens in this telescope. And you need to understand also that the instrument is not physically here. The instrument, the HARPS instrument, is located in another room, is totally isolated in another room, in another floor of this building. Okay. Now, the 360 started operations in 1977. And at that time, it was a challenge for the engineering, and it represented the great mission of ESO as an organization. Uh, so essentially, European astronomy was gathering forces from several countries to build an optical telescope in the 4-meter category, because this was the biggest and most advanced category available at that time. Now, why it was necessary to have a telescope like this? I mean, a so big telescope. Well, in astronomy, we analyze our objects through its light. So the more light we collect, the more we can learn about them. In this case, if we have a bigger mirror, we can collect more light, and of course, we can analyze more information. Okay, so essentially, we can observe to some objects that are super faint, and we can distinguish more smaller or fainter details. Okay? Now, if you want to have an idea of how this telescope can move, we have a short video to show you that. Okay. So this is the situation with the 3.6 meter telescope. As I told you before, um, this telescope is the biggest facility in La Silla Observatory. As I told you before, um, is a telescope that around the mid 70s was one of the largest telescopes on Earth. Even if right now it cannot, uh, I mean, cannot do the same like other bigger telescopes, it's still a very useful instrument, a very useful machine for some specific scientific purposes. And in this case, for example, we can search for exoplanets, I mean, for planets orbiting other stars. Okay, we are going to finish the explanation of the 3.6 meter telescope now. So we are going to go outside, because now we need to continue with the next telescope, with the next stop. I mean, the NTT, the new technology telescope. But before that, I want to highlight the main differences with, in this case, with the domes. So, for example, if you consider both telescopes have a mirror that is almost the same in size. The entity is here. You can see the dome is very different to this one. Okay, this one is something like a classical dome. Okay, it's very high. Okay, but this one is different, and you will see it later. And you can see the difference in a few moments. Now, the entity was inaugurated in 1989, and the dome is a very small and compact dome. The design is something like an octagon shape, and there is a system of flaps. This represented at that time an evolutionary leap in the construction of telescopes because this was very useful to host some instruments in smaller structures, lightweight structures, and also much more efficient in terms of the circulation of the air in the interior. So essentially, with the NTT, it was not necessary anymore to have something like this. I mean, to have this kind of big and not so efficient dome. I mean, this classical dome. Okay, so we are going to visit the entity, but before that, I don't know, Hector, if we have any question so far.
We don't have any questions so far, so let me ask you a very common question that we have in the tours. What kind of maintenance is necessary for the telescopes?
Yeah, in order to keep the telescopes in optimal shape, we need to do some maintenance on the mirror, and the most important maintenance, and I will enter again to the 3.6 to explain this. The most important maintenance has to do with the mirror because we are in the desert, we have dust, so sometimes we can have some dust coming here. So one of the main, one easy maintenance involves to use a carbon dioxide snow. This is something like a foam. So usually a couple of engineers can spread this carbon dioxide, and this can help to remove the dust. Okay. To do that, you need to tilt the mirror, I mean the telescope a little bit. So when you are doing this process, essentially the dust will fall to the ground by gravity. Okay, this is one easy solution. In the case of the 3.6-meter telescope, you also have this system of tabs. Okay, now it is more difficult maintenance is something that you need to do about every 2 years, and you need to extract all the mirror from the telescope. I mean, you need to remove the mirror from here, you need to extract the mirror to the outside, and you need to do something that is called a recoating. A recoating is essentially to change the reflective surface of the mirror. And this is something interesting because this mirror is vitroceramic, is a vitroceramic material, and the surface is a very thin layer of aluminum. So this layer of aluminum, this is something that you need to change every 2 years. The recoating involves to replace, to remove and put a new layer of aluminum. So you are replacing the original aluminum, and essentially the mirror will look like a new mirror. That's the main purpose of the recoating. So this process usually takes a few days, and when the mirror is ready, you can return the mirror to the telescope. You need to reinstall the mirror in the telescope, and the telescope can start working again. Of course, in order to extract a mirror and to move the mirror to a recoding facility, you need to use some special machines and vehicles. But this is a standard process in astronomy, and well, of course, we have been very successful with this because La Silla has been operating for more than 50 years, and we have been using the same original mirrors, but we are changing the reflective surface. So that's why we can keep using the original mirrors, because we need to change only the surface, not the main mirror cell. So that's it about the maintenance.
Okay, thank you, Fred. Okay, so maybe before we continue, you can also tell the people viewing us about how to visit the observatory in person.
Yeah, sure. La Silla and Paranal, we have a public visits program, and in this case, you can visit La Silla Observatory um, on Saturdays. Okay, so you have the chance of visit La Silla on the on Saturdays at 10 a.m. Uh, and this is okay. So something important to know about this. You need to do the first step is to do is to do an online booking. Okay, you need to visit the ESO website, ESO.org, and you need to find the section of the public visits to the observatory, and La Silla specifically have visits Saturdays all year round at 10 a.m. It's always recommended to arrive at La Silla at around 9:30, and you need to consider that the closest city is La Serena, so you need to consider something like 2 hours, 2 hours and a half of travel time. The tour will start at 10 a.m. and will finish around 1 p.m. Saturdays from September to March, specifically, we have another tour at 2 p.m. Okay, and this tour will finish around 5 p.m. And we have tours on also on Sundays, but this is only from April to August, and this is a tour at 2 p.m. So essentially, you have different options, but in all cases, you need to do an online booking. The visit is completely free, but you need to arrive with your own means of transportation. So essentially, you need to go with your car or with a friend or etc. But the visit is totally free, and you have the opportunity to visit the telescopes during the day, and you have the chance to have an English tour or Spanish tour. So that's it.
Okay, thank you. And I would like to invite our viewers to send us any questions or comments if you have any, and we'll have a second round later in the tour to answer them. And for now, we can continue to the next stop.
Okay, thank you very much, Hector. We are going to visit now the NTT. Okay, so here we are, and as you can see, if you remember the structure of the 3.6-meter telescope, I mean the big dome, and if you remember the person inside, the person looks very small. So in this case, the situation is totally different because here you have a view of the NTT telescope in the inside, and you can see that this telescope looks much more compact. Okay, this telescope is located in the NTT dome, and you can see that this dome is very different because it looks smaller, of course, and in addition, all this building, all this area of the building is essentially attached to the telescope. So, for example, when this telescope needs to rotate, it's not only the telescope rotating, it's all the building rotating. Okay, so that's why. I say that is like attach the building to the telescope. Okay? Now, this telescope, of course, can be tilted. We have an inclination here if we want, but the rotation system involves the telescope and the dome. Now, you can see a door here, so you can estimate more or less the size of a person compared to the telescope. Do you see? So essentially, it's a much more compact enclosure, it's a much more compact facility, but the important thing is that the mirror is almost the same like the 3.6 meter telescope. In this case, the diameter of the entity is 3.58 meters. Do you see? So it's very, very similar to the 3.6. This one is 3.58 meters and is also different weight, different different weight and different thickness. So, for example, something I forgot to mention before, the 3.6 meter telescope, I mean the telescope there is 53 centimeters in thickness. I mean the 3.6 meters, and the weight is about 11 tons. This is the equivalent of 2 African elephants. Okay, so remember, the 3.6 meter telescope is the mirror, the 3.6 meter mirror, 53 centimeters thickness, 11 tons of weight. This one is um, is something like 24 centimeters thickness, and the weight is about 6 tons. So it's something like 1 African elephant. So do you see? The situation here is much more simple because you have a lightweight mirror, you have a mirror that is not so thick, but it's essentially the same principle. I mean, this is a concave mirror as well. This mirror is concave, and the surface is also aluminum, so it's very, very similar in this case. The only things that are different are the size of the enclosure, the weight of the mirror, the thickness of the mirror, okay, and of course the diameter, but it's very, very similar. I can show you from the other angle, so you can see you can see the perspective from the entity. Now, coming back to the mirror, if you look at the mirror here, you can see that this mirror, maybe the concave shape is visible from here, okay? Now, but there is something else that is very, very important about this mirror specifically in the entity, because as you can see, there is something just underneath, okay? We have this kind of, let's say, structure, and there is something inside. The things inside are a kind of pistons. We have a kind of piston that is the technical name is actuator. Okay, we have 75 actuators on this mirror. Why we have that? Because the actuators are providing a small pressure on the mirror. I mean, the mirror is can go a little bit up or down, okay, in order to keep the perfect concave shape. Because you need to remember that even if this mirror is less heavy than the mirror in the 3.6 meter telescope, it's still a very heavy mirror. So when this telescope is tilted, just because of gravity or physics, the concave mirror here can suffer distortions, deformations. Essentially, this kind of distortions can affect the concave shape of the mirror. And if you affect the concave shape of the mirror, you are affecting the quality of the final picture. So in order to preserve the quality of the final picture, we are using the actuators here. The actuators are compensating any distortion on the mirror. That's the main mission of the actuators. Now, all this kind of actuator system is part of a technology that is called active optics. So the active optics technology was developed by ESO and was implemented in first place in the NTT telescope. And right now, today, is implemented as well in the Paranal Observatory and almost any modern observatory. So that's why this was very, very important at that time um, in order to preserve the quality of our pictures. Okay, so this is about the NTT. Now, something else I want to talk about is where are the people? I mean, the astronomers. Well, in La Silla, we have approximately 30 people, and all of them are working in different telescopes and tasks. Now, in particular, the scientific and technical staff are not here. They are not in the telescope. They are not here. They are not in the 3.6-meter telescope. They are in another separate location. So essentially, all this place is in darkness at night, and we have no people here, no scientists is here. They are working from a dedicated place that is called the control room. And we can see a short time lapse of the control room to understand a little bit better what happens in this place. So you can see in a few moments, here we have the control room of La Silla. So as you can see, we have two workstations. The workstation to the left is for the NTT, and the workstation to the right is for the 3.6-meter telescope. And you can see different computers for different purposes, and you can see some people working there. And you don't need a lot of people actually, because you need usually the telescope operator and maybe one astronomer. The telescope operator is the person in charge to move the telescope remotely, and the astronomers, if we have an astronomer, the astronomer can decide the next steps, can decide something about the instrument, etc. But essentially, they are working from here all night and looking at the computers to receive the information, the pictures from the telescopes. Okay, so at this point, all of you have a lot more information about the observatory and the people working here. So now I want to invite you to take a look at the main scientific milestones from all ESO observatories. I mean from La Silla, Paranal, and Chaknatov. So please pay attention.
Observations with ESO telescopes have led to many breakthroughs in astronomy, and over the years have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it. Stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history. Elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so that was the top 10. I hope you enjoyed. This was just a sample of all the scientific discoveries possible with the ESO telescopes. So now we are going to moving on with the tour. And as you can see, we are in the middle of the night. In this case, the sky is completely clear, no moon, and you can see the starry skies, and it's very, very beautiful. So now we are going to dedicate some time to explore some night objects and regions of the night sky from La Silla. By the way, this is the entity, okay? The entity at night. This is the part of the dome I told you that rotates with the telescope. And from here, I want to show you some interesting objects of the night sky. So, for example, just next to the entity, to the left, from our perspective, we can see a constellation, a very popular constellation. This constellation is Orion, and you can recognize Orion because of those three stars here. The stars are somewhat aligned, right? Um, in the mythology, Orion is a hunter, okay? And those three stars represent Orion's belt, okay? Um, in Spanish, this configuration is called the Tres Marias or Three Marys, okay? Now, Orion is a constellation that is visible from the northern hemisphere and the southern hemisphere. So essentially everyone can observe Orion, and it's very easy to recognize, as I told you before. But in addition to those areas, the three stars, you have something else just next to the Orion's belt. This object here is the Great Orion's Nebula. This is a star-forming region that is very bright, is very big, is possible is possible to observe the Great Orion's Nebula even with your naked eye in a clear and dark night, of course. You can see it like something like a distorted spot in the sky. And of course, you can observe this nebula with even with binoculars or even a small telescope. Okay, so in this picture, you can see that Orion is almost setting in the sky. Now, if we continue moving up, you will see a very bright star. Now, this bright star right here is actually the brightest star in the sky. And this star is named Sirius. Okay, Sirius is a star that belongs to a constellation called Canis Major. And Canis Major in the mythology is essentially one of the hunting dogs of Orion. So you can say that the constellation of the brightest star in the sky is connected to Orion right here. And this area is also visible from the northern hemisphere and the southern hemisphere. Now, if you pay attention, you can see that both Orion and Sirius are visually close to this kind of uh, band of light. I mean, this area has more concentration of stars, can you see, if you compare with this area or this area. So all this area here, okay, all this bright band of stars is actually one of the arms of the Milky Way. So you can see that this arm of the Milky Way has a lot of nebulas, dark nebulas. I mean, the red areas of hydrogen. So it's essentially one interesting area of the sky because it contains several deep sky objects. Now, the Milky Way, of course, is our galaxy. Our sun is part of the Milky Way. So, from our perspective, when we look at the Milky Way, we see the Milky Way as something like a flattened disk. Okay, um, but from the southern hemisphere, in particular, in winter months, in the summer, sorry, in the southern hemisphere, I mean, end of May, June, July, you can see even the center of the Milky Way, and this is very, very impressive because you can see all the Milky Way all night. But this is only possible from the southern hemisphere. Okay, I will change the position now, and I will show you another sector in the sky because I want to focus on a couple of spots. I mean, this and this. So what is this? Those are the Magellanic Clouds. Okay, this is the large Magellanic Cloud, and this is the small Magellanic Cloud. They are not clouds actually; they are galaxies. They are galaxies with an irregular shape, and they are actually satellite galaxies of the Milky Way. So they are orbiting our galaxy. The name is because well, the first person who was able to record them officially was Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So at that time, it was impossible to know what a galaxy is. So that's why it was recorded like clouds. Okay, but now we know that they are galaxies with an irregular shape, and they are orbiting our galaxy, the Milky Way. And also, they are only visible from the southern hemisphere. So you cannot see this from Europe. You cannot see this from USA. So you need to be in the southern hemisphere. In particular, in the north of Chile is, of course, is a very, very good place to observe this. And near here, we have other important region of the sky. We have the smallest constellation in the sky, and the smallest constellation is right here. This is the Southern Cross. As you can see, it looks like a cross, right? This cross is essentially in another important area of the sky, because as you can see, you have another dense populated area full of stars, full of nebulas, full of these deep sky objects, because you have another arm of the Milky Way. Do you see? So again, the Southern Cross is the smallest constellation in the sky. It's only visible from the southern hemisphere, and in this particular picture, it looks a little bit tilted. Okay, so sometimes it's tilted, sometimes it's in the right position, sometimes it's a little bit more tilted, but it's their usual view from here. And just to finish this view of the night sky, I will come back to the 3.6 meter telescope, because in this particular picture you can see that the Milky Way, I mean the center of the Milky Way, is rising from the horizon just behind the 3.6 meter telescope. So this area, of course, is very, very beautiful. You have something like a wide center here. You have the constellations Scorpius, Sagittarius. So this is the area that I told you before is visible all night from the southern hemisphere during the winter months. I mean June or July. I want to show you another perspective of the 3.6 meters, 3.6 meter telescope. I mean, I want to show you the 3.6 meter from the platform at night. So again, this is a very beautiful picture here. This is not so beautiful. This is the light pollution from La Serena. But fortunately, it's not so complicated because it's very low in the sky. But of course, it's important to keep light pollution under control. And over there, you can see the other telescopes of La Silla. And we are about to finish this tour going there, because I want to show you first La Silla Road at night. This is a short road to connect all the telescopes. I mean, all the small telescopes here, the NTT, the 3.6 meters, because we need to communicate all the telescopes by this road. And this road will finish in La Silla Hotel, because this will be the last stop of this virtual visit. La Silla Hotel is the place for all the people working in this observatory. I mean, in this place, we have the bedrooms, we have the restaurant, we have all the necessary facilities for the people working in this fantastic observatory. This person here is the astrophotographer in charge of all the pictures you was able to observe during this virtual tour. And this picture in particular was taken in winter months, and I can show you that in this picture, the center of the Milky Way is about you, is in the zenith. So this view is only possible from the southern hemisphere, and that's why this is a very, very interesting place for astrophotography if you are living in Europe or North America. Okay, I will finish here. So this is the main explanation, and I don't know, actually, we have any last question.
We have a couple of questions. So here we have some questions. Is there a way to get a tour directly to the observatory? And they're asking from Asia.
Oh, well, I am not aware if there are some kind of touristic package from Asia. Or I don't know what country in particular is this person, but uh, I know that some astronomy tours are departing from Europe sometimes to visit specifically the north of Chile to visit some observatories because yeah, I understand is far from something in Asia, but I'm not quite sure if there are some specialized tours like astronomy tours from Asia, but I know that there are some options from Europe and from USA. That's the information I have so far.
Um, and we also have a question here from Jordi. Where do you have adaptive optics? Which of the telescopes?
Well, La Silla is mostly using active optics, in particular in the NDT. Uh, I can say that adaptive optics was used in La Silla at some early stages. So, for example, in the 3.6 meter, the 3.6 meter telescope did use some adaptive optics systems for some experiments. Okay, and I think that some specific smaller instruments right now are using some kind of adaptive optics, but essentially adaptive optics was mostly tested around the 90s, and but now is more mainstream for Paranal, for example, and for the next ELT. But La Silla is mostly using active optics.
Okay, and that was our last question. We have a couple of greetings. We have Joshua Alexander Christian saying hello, and we have Sway Graven, a regular viewer. And that's it for the comments side. So I guess we can just start finishing things up. For my side, it was a pleasure being with you today. I remind you that we're doing these tours every Saturday. We are alternating between doing it in Spanish and English, and also between the Sea Observatory and Paranormal Observatory. So keep an eye out for when the next tour is going to be, which language, which observatory, so on.
Thank you very much, Hector. So please remember that all these visits, informations, pictures, etc., is available on the ESO website, so you can explore more in our website. So yeah, please remember and pay attention to the ESO social networks to know more about the next tour in Spanish or English, Panel or La Silla. So I hope you enjoy it, and on behalf of ESO, I want to say thank you very much for your virtual presence. So thank you and see you next time.